Hello there and welcome to one video of my series explaining electronics parts. As always, I'm going to give you some basic information on the left hand side of the screen, and afterwards I'm going to give you an exact example looking into a datasheet. Today we're going to talk about Schottky diodes. Besides Schottky diodes, there are also different diodes like PN or NP junction diodes. These are the diodes we usually use. Also, there are Z or Zener diodes and light emitting diodes, and we know them as LEDs. So there are certain things to consider when making use of Schottky diodes in your electronics designs. Pros or advantages of Schottky diodes are that they have a lower forward voltage. That means that less voltage is dropped across the diode. When we are in high current applications, this means that we lose significantly less power in our entire design, and our entire product will be more efficient, lose less power, and probably live longer because less temperature rise is achieved. This is also why Schottky diodes are usually made to carry higher currents. They're made to be used in high power applications and carry a lot of current. For example, when we compare a Schottky diode with a voltage drop of 0.35 volts to a normal diode with a voltage drop of 0.7 diodes at 1 ampere, we already are losing 350 milliwatts less of power. We're creating less heat, and we're making the design twice as efficient in a way, or we'll lose half as much power across the diode. Another advantage is that they switch faster than normal diodes. They can be used in high-frequency switching applications, like for example DC-DC converters. Disadvantages or cons of Schottky diodes are that they are usually designed to withstand only low voltages. Normal diodes are designed to withstand voltages of up to 1000 volts, and Schottky diodes usually have their issues reaching 100 volts. Also, they have a high so-called leakage current or reverse current. This means that the diode is not perfect. To tell you first off, no diode is perfect. Diodes are used to make current only go into one direction, but no diode can really do that perfectly. We always have a certain reverse current. With normal NP or PN junction diodes, this reverse current can be as low as a few nanoamps. But with Schottky diodes, it always is at a few microamps, if not milliamps. And also we have to consider the temperature, because this factor, the leakage current, is highly temperature reliant. It means that when we have a low temperature, the reverse current is very low, but if we increase the temperature, the reverse current can easily increase by a factor of a few hundreds, if not thousands. Besides that, we also have to consider that Schottky diodes are more expensive than normal diodes. But if we have to use them in a use case, there's no way around it, and don't try to skimp on certain parts. So now we're going to continue with where to use Schottky diodes. Usually they're used in DC-DC converters, or sometimes in protection circuits where reverse current is to be protected against. Like for example, reverse polarity on some devices. You should not use diode for that. You can use a more intelligent MOSFET circuit, but we're not going to talk about this here. Just Google reverse polarity protection MOSFET and you will get your circuit. Schottky diodes could be used for bridge rectifiers, but usually they're not, because they have a high reverse current, which means the bridge rectifier would actually have a standby current. Also, they're more expensive, and no one wants to pay €2 for a bridge rectifier, which might drop less voltage across it, but well, that's usually not what people do. They try to keep it cheap, and if you don't need high currents, you're just not going to use it. Also, Schottky diodes are used in battery-powered applications in general, where voltage drop is very critical and is to be kept at a low level. Not all designs require this. Many designs can be adopted to work with normal NP or PN diodes. And this can also have advantages, because when we design, we should take certain things into account, like for example, that the reverse current can render many devices or circuits unusable or very glitchy. Certain things can occur. You never know what's going to happen if the reverse current is not taken into account the correct way. If the reverse current is too high, certain circuits will glitch, turn on, turn off, and show a very obscure behavior which cannot easily be reverse engineered. So if you have Schottky diodes in your design and something is not working right, you probably have to blame them first. Also, take into account the high price. Not all management decisions will be okay with paying €1 extra for your device just because Schottky diodes could increase the efficiency. But you will have to calculate it out and find out if there's another way to do it. Usually you try to make it the most simplest, most reliable, and the cheapest solution possible. Just try to get different considerations into account. Also, well, you don't need Schottky diodes for signal pushing or protecting signal wires. If there's not a lot of current involved, don't use a Schottky diode. Usually it doesn't make sense. Well, now people are gonna say, oh, Schottky diodes, they have less voltage drop, and that's correct. But if you are looking into the datasheets more deeply, you will find out that the voltage drop of a Schottky diode or normal PN or NP diode can be close to 0 volts if there's not a lot of current being drawn. That means that if you don't use it for power applications, you should not use it at all, probably, because the voltage drop with normal diode will also be in the millivolts if you're only using it to push signals and carry a few microamps. And this is the thing. If you use Schottky diodes to try to carry signals, and the signals in one direction, which they should only go, are only exceeding a few milli, if not microamps, the reverse current is so high, even at room temperature, that it could just, like, be a short circuit, like not having a diode at all in your exact use case. So take that into account. And yes, the voltage drop can drop. That's what I just told you. If you don't use a lot of current, the voltage drop will be even lower. In one case, this can be useful. In the other case, it can be very critical because some people might use it to drop voltage. Like, for example, we have to achieve a voltage of 2.7 volts from a source of 3.0 volts. So what do? Well, we could use a linear regulator, a low dropout regulator, or a switching regulator to achieve that, but we could also use a Schottky diode. Some people would think, but you cannot. You cannot if the current draw is not constant and high enough. If the current draw of the device at 2.7 volts is low, the voltage will increase to almost 3 volts. And take that into account. Many devices can go to standby, draw a few microamps, and the Schottky diode will increase the voltage at its basically output at the 2.7 volt device higher and higher. It could potentially damage the device or render it unusable. So take into account that the voltage drop, can get close to 0, and thereby make many things not work the way. Now we're in the second part of the video, where I'm gonna jump into a datasheet and give you some more close to reality examples of a Schottky diode. We have a B series Schottky diode here. They are usually used in DC-DC converters if you have some kind of XL semiconductor DC-DC converter from China. You're most likely seeing a diode with an SS on, SS56 or SS54 or SS31 or 32, or one with B5 something C or B3 something C. The naming scheme is as followed. First, there is some kind of model number, and in the end, there's also some kind of model number. These things usually you don't have to take into account. What you have to take into account are the numbers in between, the numeric value. The first number is gonna tell you the amperage. Is it 1, the diode can withstand 1 amperes. If it's 5, the diode can withstand 5 amperes. And here we're talking about continuous currents, but only under certain situation and conditions. We'll have a look into the datasheet and find out which things we have to consider when we try to use it at its maximum. The second two numbers are going to show you the maximum voltage. 20 means 20 volts. The maximum voltage applied to the diode should be 20 volts, otherwise it cannot be guaranteed that it works as intended. It could break the diode, it could just short circuit it. Many things can happen. 60 would be 60 volts. So the B560 or the SS56, same naming scheme there, are made to withstand 5 amps of current at up to 60 volts. We can here see that the 20, 30 or 40 volt variants, so the 2, 3 or 4 variants, SS20 something, or SS something 2, SS number 3, SS number 4, that means SS underscore, which is some kind of numeric value, and then 3 or SS underscore 4 or SS underscore whatever, 2 in this case, they have a voltage drop of 0.55 volts and a reverse current of 0.5 milliamps. So now you see, well, reverse current of 0.5 milliamps, that's perfect, and just a voltage drop of 0.55 volts, that's also very good. But take into account that this is at laboratory conditions. This is at 20 degrees Celsius, a peaked frequency, probably a diode with good binning. You never engineer down to the facts in the datasheet on the top of it. You dive more into it and find out that your device is probably, or the diode you use, is probably not as good as it is marketed on the first page. This is not with this company. It has nothing to do with the company. Many companies produce this exact diode and other parts which follow the same scheme. Just don't get tricked on by just believing what's on the first page. And yet, the series with 50 or 60 volts capabilities have a higher voltage drop, but the same reverse current. More data is here. We can see a peak non-repetitive forward surge current, which is 100 amps. So for 8.3 milliseconds, you can push 100 amps through it, but non-repetitive. It's just probably a short turn-on pulse where something is going to charge up a capacitor. So take into account that this current will not be there for somewhere close to 8 milliseconds, and probably something is wrong if you draw 100 amperes for this diode. You have poor DC traces on your board. Well, if this is gonna to occur, you probably have a different issue. Yeah. Other things. For example, the thermal resistance is 10 degrees Celsius per watts, which is in this case very good. They have a big package, and per watt of drop, they only heat up by 10 degrees Celsius to the terminal, the junction to the terminal. That means the terminal, the metal pads on the diode, are usually 10 degrees colder, or heat up 10 degrees if there's 1 watt more of energy dropped across the diode. But the junction heats up about 50 degrees in relation to the ambient, and that's usually what you should consider. If you don't have extra thermal things taken into account, consider this value, and make sure that at an environment temperature of about 40 degrees, your junction should not go over 90 degrees Celsius, so you should not drop more than 1 watt over this diode if there's no extended thermals, or if you don't want to risk heating up the diode to 120 degrees at its junction. Now we come to a more interesting part, which actually shows you the leakage current or reverse current at different temperatures. Right here you can see that the normal reverse current is 0.5 milliamps, but if you heat it up to 100 degrees Celsius, which can easily happen, like we just saw, you just drop 1 watt over the diode, and you're at 90 degrees, so close to 100 degrees Celsius, and suddenly your leakage current is not 0.5, but it's 20 milliamps. This means, if you take it to relation, if we drop 0.55 volts on this 20, 30, or 40 volt series, we cannot draw more than 2 amps, or if we draw 2 amps, so 0.55 volts at 2 amps is roughly 1 watt. We have to take into account that now we have a reverse current of 20 milliamps. So draw 2 amps through 5 amp diode, and it's not 0.5 milliamps, it actually is 20 milliamps of drop. Just keep that in mind. This also is a capacitance in picofarads at the voltage of 4 volts and 1 megahertz switching frequency. If you don't go to high frequencies like a megahertz or so, or a few megahertz, you usually don't have to consider this. If you are going with higher frequencies, you probably should stick to the datasheet of the device which is achieving the high frequency. Like, for example, if you're using a DC to DC converter, use the diode which is specified in the datasheet. Then you're making sure that it's just going to work and you're not having weird glitches. Right here we see more graphs which show certain relations of yeah factors, and yeah, right here we can see that if we heat up the junction to around 150 degrees Celsius, we have a very high reverse current, achieving almost 100 milliamps if we increase the reverse voltage. If we increase the voltage among the diode. So many things to take into account, and especially with Schottky diodes, please make sure that the temperature is right and that the reverse current is not as high and that you don't push too much current through the diode. If they show you 5 amperes continuous, you have to take many thermals into account, have big pads, have a lot of copper per square inch or per area, and probably also consider additional cooling. This package is not designed for additional cooling. You might find Schottky diodes with a TO package with a screw hole, which you can attach to heat sinks, and this will make it more easy to cool them down and make sure that you don't have too high of a reverse current at higher currents because the overall device is cooler. But yeah, just make sure that you take these things into account, and yeah, hope to see you in the next video. Goodbye.